Good evening, everyone. We'll be starting in a few minutes. Okay, so this will be the review of the session, means week 10 of the NPTEL series on reinforcement learning. We'll look at a few problems, and I'll be also going through the adjoining theory that is required to solve these problems. Okay, so starting off with the first question. So consider the update equation for SMDP learning, and which of the following are the correct values for A and B? So RK is the reward received. So Rk is the reward received at time k, time step k, and gamma is the discount factor. So what is the formulation of the SMTP Q learning is what we need here. So so let me just explain that. So first let me go through what is SMDP. So SMDP is useful in the case of the some more background is required, I guess. So first of all, the concept of hierarchical RL is important. So in hierarchical RL, you are dividing the you're not trying to learn the problem at one step, one go, but you're dividing it into sub problems. And so we're trying to find a structure in the state space and dividing into sub problems and learning each of them separately or with some correlation between each other. So that is what we have here. And so just one example is this. So from we have to go from one side to another side, one to two, and you're not given any end goal in means like where in two you have to reach. So what will be supposed to do is like if you are below this hole, then you go up. If you're above, then go down. Similarly, okay, uh, okay, um, and suppose you're given a goal here that you have to reach this point optimally, then what you will do is that you'll take this path and then move right. Okay, so that will be the one. Okay, so so first one is the recursive way. Means you're just looking at going to that second compartment without looking at the end goal. Okay, and the the second way is the hierarchical way because you're also looking at the end goal while taking action for the action in the first block. Okay, so and another so this is the so the first way of doing is called the recursive optimal way, and it is the hierarchical optimal way. If you ignore hierarchicality, that is called the flat optimal way. Okay, so for recursive optimal way, we have the semi-Markov decision process. Uh, so here, so the best difference between Markov decision process and semi one is that there is a time delay between actions are taken and the results, and that is the state change that happen is the time delay on that, or you can interpret it like you will take action after some time, or you will take action, then the result will happen after some time. So whatever, so there is time delay between them. So in typical Markov decision process, what happens is that you have the state st, and this is at, this goes to st plus 1, and the reward is rt plus 1, this goes to at plus 1, st plus 2, rt plus 2. Okay, so these are the state action reward structure, or it's called the probabilistic graphical model of this. Okay, and but in the case of SMDP, what happens is that you have state ST, then you take an action AT, then you're taking an action AT, but there is a time delay of t plus lambda. Okay, so t plus tau. Okay, after t plus tau, the state changes st plus tau, and the discounting factor is gamma t plus tau. The reward at this point is r t plus tau. So it goes on like this. This is at plus tau dash. Okay, this becomes st plus tau dash plus tau. Okay, and this tau is called the holding time. Okay, uh, the next thing is, so the SMDP notation is S A P and R. Okay, this is how you define the process. Uh, next thing, another thing is, so this is the transition probability from state S to S dash, and conditioned on action A, and also one important thing is this tau here, which is the uh, holding time here. You cannot ignore this one here, because like after the time duration or the lag determines which state or the condition or the reward at this state. Okay, so that is why this tau, the holding time, also comes uh, as a parameter in the transition probability. Okay, so this is useful for RL applications because mm, we see this tau as related to, means tau, this S dash that we reach here depends on the tau. Okay, so that is how we see it. Okay, so if you expand it in the form of the Bayes rule style, okay, okay, conditional probability, then you will have that S dash depends on tau. Okay, but the classical formulation, the historically it was done, is S dash depends on transition from S and A, and so we separate these together. Okay, and so S dash is independent of tau, tau is independent of S dash. Okay, but this formulation is more useful in RL setting. Next is SMDP Q learning. So what is the Q learning formulation for SMTP? So this Q STAT, this will be T plus 1, alpha times R dash T plus tau, and this is the discount factor. Okay, so but In this case of SMDPQ learning, the discount factor is raised to the power tau here. Tau is the holding time here, okay, which is not in the case of simple Q learning. Okay, so max A dash Q S dash A dash minus Q S T A T. Okay. Uh, Now what is RT plus tau bar here? So it is the discounted return. Okay. So the formulation for that is, so tau we consider here a discrete. Okay. So 1 to tau values. Okay. It 1, 2, and 3, like that up to tau. It has progressed. For each time step, we multiply with a discount factor gamma. Okay. So it's gamma square RT plus 3 dot 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 gamma to the power tau, tau minus 1 r t minus tau, t plus tau, t plus tau. Okay, so this is how it is formulated. Okay, so we have got it now. This is enough information needed for solving this problem. So A is this discounted reward here, discounted return here, and B is given as the gamma to the power tau, which is the discount is raised to the power tau before multiplying with the next state and action uh, Q function. Okay, so that is why B is the answer. Okay, okay. So we have a SMDP in which the next state and the reward only depends on the previous state and action. So that is what they say. Like, so we train with conventional Q learning and this SMTP Q learning, we will end up with the same policy. That is the claim. That is not true actually, because in this problem you could see that gamma was raised to the power tau. Okay, so even if this does not depend on tau, the transition only depends on the previous state. Okay, then also the tau factor will be there. Okay, which will, discount will be different in the case of SMTPQ learning. Okay, so this is the answer. Any doubt at that? Okay, moving on. In So we've moved on to a different topic now. So hierarchy of abstract machines. Okay. Uh, so this requires some explanations. Okay. So, hierarchy of extra abstract machine HAM is there. Okay. So, the research into this, the pioneering work was done by Parr and Russell. Okay, and in this, it comprises of uh, four main states here. So first is action state, and then call state, choice state, stop state. Okay, so action state denotes that you have reached to a state where you have to take a preliminary action. Okay, so here there's an important concept. So the important action is called that. So this preliminary action or like action, this comes from the concept of options here, and it is part of hierarchical RL. To explain that, so we have options, which is denoted by Z0, pi 0, and B0. Okay, so so you can say it is like a kind of solution to the sub problems, encapsulating as a single action. So what do you mean by that? That you have taken repeatedly different actions and reached to a state. Okay. So combination of all these actions is called the macro action. Okay. And each of these is called a preliminary action. Okay. To learn this sequence of actions required to achieve a goal or state, in this case, the desirable state, this sequence of action is determined by a policy. The policy in this framework is called an option. Okay, so this is the meaning of the option terminology. And further, uh, so there are three components in options. The initiation phase. Okay, so so the problem initiates, or the algorithm initiates from a set of states that are given. Okay, each of one of these. Okay. So another is the policy to do the action. So this is denoted by I0, okay, and the policy to do the action, okay. Learned policy is the pi 0 here. Termination condition, beta 0, okay. This is denoted by 0 or 1, hence yes or no. But does this terminate or not? Okay, and okay, so this is the concept of options, which actually encapsulates the all the smaller subproblems and aims to represent it as a bigger problem with an action which are which are uh, longer range, and so these actions are called macro actions here, and the policy that is learned for this actions to be taken is called the option. Okay. Next, we have the concept of Markov options. So, Markov options is formulated as such that so you have a policy pi 0 here. So the policy pi 0 is only defined for a specific state. Okay, state S. So what does it mean? That whenever you at a whenever you reach a specific set, say specific state, say S0, uh, the policy will be pi 0. Okay, policy pi 0 will be applicable. Okay, without any change, or whatever with the temporal situation does not matter. Okay, this is what we called Markov options. Okay, so following up on that, we have semi-Markov options. So I was covering Markov options. The policy pi 0 is only dependent on the state S0. So means what it means is that whenever the state S0 happens in the process, the policy applicable will be pi 0. Okay, so that is called the Markov options, and it does not depend on which sequence of actions that we have gone through to reach the state S0. Um, and following up on that, we have semi-Markov options. So, so we start from state S0, following up with different actions, different states, and reaching to state 0 again. Okay. So in semi-Markov options, the policy pi 0 defined is dependent on all the sequence of states starting from the point of concern state S0 and reaching back to state S0 again. So this is called the semi-Markov options. Okay. So it depends on the state sequences from the sequence state of our concern and reaching to that state again. Okay. Uh, so the policy pi 0 depends on the sequence. Okay. Uh, now we come back to a hierarchy of abstract machines. So here it is. Uh, so here, whenever we reach a state that we have for that specific state, we have to take an action, a preliminary action, not a macro action. So that state is called the action state. And call state. So as you can understand, in this we have several smaller problems arranged in hierarchical way. So this goes and this goes, or something like that. Okay. So call state defines that when you reach this state, you have to call another smaller machine, okay, hierarchical machine, and then that machine will take whatever action or call or whatever it wants to take, okay. So choice state is the complicated one here. Uh, hard to understand. So it is a so it takes non-deterministic transitions, okay, transitions to one or more states, okay. So what does it mean that it wants to pass a message or something to all the states, some of the states, okay. That is called choice states. It's not explicitly calling one of the states, but some common information that needs to go to one or multiple states at a time. So that is called the choice state. Stop state defines the so here stop state is not does not define the whole machine. It defines one of the smaller machine and asks it to stop, okay, and gives back this message to the previous machine which has given the call state to the present machine. Okay, so that is what we call as the stop state. Okay. Um, okay. So our question is, so you're given a hierarchical abstract machine, and what will be the immediate reward received between the two choice states? So there are two choice states here, and so what will be the immediate reward? So the point of this is that the actions taken in between the two choice states, whatever the reward that is accumulated because of these will be the uh, immediate reward in this case. Okay, accumulation of immediate rewards of core MDP between these two choice states. Okay, this is the answer. Okay. Further, just give an example of the situation when we use the hierarchical abstract machine. So these are the blocks. Okay, so these blocks you cannot pass through. Okay, so there are 300 or 400 of them. Okay, and there are also smaller obstacles here. Okay, repeating here and there, not all in one line. Okay, now what happens? A person has to find some find something, maybe treasure or something, has to go through this maze and reach there. Okay. So the point of this problem is that 300 to 400 blocks are there, but you can see that they are repeating themselves, almost repeating themselves. Okay. So this can be formulated as a hierarchical RL problem, and so you can define an abstract machine for that. So what we do here is that what we do here is so these each of these blocks is one machine. Okay, and so this is how we define. So follow wall is there, okay, and you have this. So whenever you hit an obstacle, okay, so then you have a choice state, okay. So if it's first of all you start from a point, okay, then follow wall. So you have to follow the wall so that you can reach to your destination. And whenever you encounter an obstacle, you have choice to back off or or uh, keep continuing in that direction, moving beside the obstacle. Okay, so this is something like this. And non-deterministically, you can also back off without any obstacle stopping you. Okay. Whenever you encounter the final reward, you stop. Okay, and that is when the process stops. Okay, this is one example for hierarchical abstract machines. Okay, so this is our problem done. Okay, on to the next problem. So I'll take a little break here, and we'll solve the rest of the problems after this. Okay. Okay, so continuing. So what is true about Markov and semi-Markov options? Okay. So Markov options, the policy depends only on the current states. That is correct. Semi-Markov options, the options policy can depend on only the current state. It can, okay. So just a specific situation is talking about. So in semi-Markov options, so as you know, it usually depends on all the states that are involved. Okay, but if there are no other states involved, it just depends on the first state that it encounters. Okay, so it can be, but in that situation also, like that it would move to the, but not in general. Okay, so I think that is the answer. So the two statements for an SMDP for an HAM, the state of the SMDP is defined by the state of the base MDP, the cause state, and the state of the machine currently executing. So, how do you define the state of a SMDP? So, the base MDP that is working inside one of the machine, that is important. What is happening there? The calls stack, the calls that will be taken one after another for of the uh, each of these each of these what you call the sub blocks or the machines, smaller machines. Okay, that is important. The state of the machine means like under which execution state it is currently in. Okay, so that is also important. Okay, so this is correct. Okay, statement one is correct. Thus, statement two is action of the SMDP can only be defined by the action states. So these are on, so that is not correct. Okay, only defined by action states, that is not correct. Then choice states and other states are in invalid, right? So these are sections will be defined by the state it is in. Okay, and choice state and everything culminating to that cause state. Okay, so statement one is true and two is false. Okay, so which of the following are possible advantages of formulating a given problem as a hierarchy of sub problems? So this is an important part. Okay, like why do we need to do this? Okay, so you'll have found these in the lectures as well, but just to brief that. Okay, so a reduced state space. So actually what you're having, that you're having two largest state space. Okay, so then you have to divide the state space into and formulating it as a hierarchical problem. Each of the each of these sub states are, you can say, a machine. Okay, abstract machine. Okay, so you get a reduced state space which you can effectively formulate a MDP, more meaningful state abstraction. Okay, so so the point is that the state or abstraction. Okay, so what it means is that uh, so the states that are uh, created, smaller state spaces, you can use them like means like this is a reusability thing, that you can use them again and again. They're like smaller blocks which can be used again and again. And okay, and so the meaningful state abstraction, what it means is that so you can encounter more than one stage at a time with meaningful more meaning attached to those transitions. Okay, that is one important thing. The temporal abstraction of behavior. So you are taking out the temporal factor that is present in the so one sequence of another, but like you are taking all the sequences together, transitions together to create a larger problem in which the temporal importance reduces. So temporal abstractions of the behavior. So all of these are correct. Okay. So in SMDP, consider the case when tau is fixed and for all state actions pair. Okay. So so the tau for all the states that as you reach for a specific actions is fixed. Okay. So we'll get the same policy for conventional Q learning and SMTP Q learning. So this is the question, okay? And the answer to this is the formula for Q learning, okay? So this is Q. So the formulation is alpha times. So alpha times R R T plus tau cap plus gamma tau times max of S dash A dash, and this is with respect to A dash, the max is, and then minus Q S T A T. Okay, and so this is the formulation for the Q learning of SMDP. For conventional Q learning, what happens is that this is the average return, that is correct. Okay, not average return, discounted return, and this tau is not there in case of conventional Q learning. Okay, so you can understand if tau is 1, this 2 becomes the same. Okay, if the of course in the return situation, we do have the okay. So if this tau is 1, then these two becomes same. Okay, so for tau 3 and 2, these are not same, so no, and then yes. Okay, that's the correct one. And moving on to the next problem, which is the following is the correct Bellman equation for an SMTP. So the correct Bellman equation is what we have asked. We are asked here. So you must understand the gamma to the power tau is very important factor here, which is not present in the Bellman equation for conventional situation. So gamma to the power tau in these two situations are there, and another thing to understand is that uh, this P S dash S comma A, this transition is invalid in the case of SMTP because we have to take account of the uh, tau as well. Okay, so that transition is important. So this one is wrong. So the what we get is the question number C. Okay, so this is all for today. Okay, so we're done with this. Okay, any doubt? Okay, thank you everyone.